Hello everyone, my name is Aayusha Yadav, and today I will be presenting on a provenance-based adaptive scheduling heuristic for parallel scientific workflows in clouds. This paper has been authored by Daniel D. Oliveira. Let's get started. These are the topics that I will be discussing. Let's start with the introduction. Scientific workflows is used for structuring or executing scientific experiments in computational environments. It is increasingly complex and now requires the uses of parallel techniques and high-performance computing. Now, in cloud computing, we know that resources are virtualized and it provides elasticity. Nowadays, it's been adopted as a platform for running high-performance and distributed applications, but in the past, it was mostly used for business applications. Therefore, there now exists a gap between cloud environment and the management of scientific experiments modeled as data-intensive scientific workflows. Scheduling and executing parallel scientific workflows in clouds is still a challenge. It is so because of the following. A. Pricing model of cloud environments. Cloud environments, they have a unique pricing model that have to be considered to fit in the budget informed by the scientists, and it is pay per use. Part B. Clouds are changing environments and they may be susceptible to performance variations during execution course of the workflow, thus requiring adaptive scheduling solutions. Now, elastic scaling of resources, hardware and software capabilities is a key characteristic of the clouds. To provide this feature, however, resources are allocated and reallocated as needed by the provider, and the users are not aware of those changes. For example, if scientists execute their workflows using Amazon EC2 spot instances, virtual machines can be unallocated or moved as the provider needs more CPU capacity. In the case of Amazon, the demand varies during the years, which means that they may need more resources to handle their Christmas rush than they do the rest of the year, for example. These moves and instabilities can provide negative impacts on the scheduling of workflow tasks. And part C, finally, in clouds, virtual machine failures are no longer an exception but rather a characteristic. Workflow scheduling has to consider reliability issues when distributing parallel tasks to execute on several distributed virtual machines. The proposed solution is as follows. This paper proposes a heuristic for adaptive scheduling of parallel scientific workflows in cloud environments. It is based on a three-objective weighted cost model that considers execution time, reliability, as well as financial cost simultaneously. Using this model, an adaptive greedy scheduling algorithm schedules workflow tasks into the many virtual machines, and a load balancing algorithm instantiates and destroys the virtual machines to meet the deadline and fit in the budget informed by the scientists. Cost model and the greedy scheduling algorithm is based on the provenance data of experiments captured and queried at runtime by the cloud workflow engine. This paper provides the following scientific workflow formalism. In this scientific workflow is defined by a direct acyclic graph named WA-DEP. Nodes A in W correspond to workflow activities to be executed in parallel, and the edges, denoted by DEP here, are associated data dependency between activities in A. Now, A can be comprised of activities A1, A2 to AN, as shown here. Let I be the input data state for activity AI. Let O be the output data produced by AI. Now, in this DEP AIAJ DS, DS is the size of the data transferred between these two activities. Given a workflow W, a set CA equals CA1, CA2 to CAK of cloud activities is created for its execution. Each cloud activity I is associated to a specific activity I, which is represented as ACT CAI equals AI. A set of cloud activities of a workflow activity AI is denoted as CA of AI. Now, each cloud activity I consumes its own input data, input CA of CAJ, and produces output data, output CA of cloud activity I. We establish the dependency between two cloud activities as dependency CA of cloud activity I, cloud activity J with DS, and can be denoted by this equation right here. A specific cloud activity CAI is modeled as CA time, where time is the total execution time of cloud activity. Data parallelism in scientific workflows is characterized by the simultaneous execution of various cloud activities of one activity AI of the workflow W, where each cloud activity I processes a disjoint subset of the entire input data, which can be represented by a fragment set F, Fi1, Fi2 to Fik. The set of fragmented output data F output K generated at each K execution have to be merged in order to produce the final result OI, which is the output I. Now, parameter sweep parallelism, what we mean by this is the simultaneous executions of cloud activities, where each cloud activity I consumes a specific subset named PVI, which is the combination of the set of parameters domain point of an activity AI to be processed. It can be achieved by generating several cloud activities of a specific activity, and each cloud activity I processes a specific subset of the possible parameters value PVI. This paper proposes a three-objective cost model. Let VM be the set of M virtual machines that composes a virtual cluster. Virtual machine is modeled as VM, in brackets network, CSI, memory, max grant factor, part grant factor, average time, previous execution time. Now, network means the network bandwidth of the virtual machine, this network right here. CSI is the computational slowdown index. Memory is the RAM capacity of the virtual machine, and max grant factor, part grant factor, and average time and previous execution time are information about the previous executions of this virtual machine. Now, computational slowdown index of virtual machine J can be represented like this. Now, P cloud activity I, virtual machine J denotes the expected execution time of cloud activity I in virtual machine J. Now, this expected execution time can be calculated as cloud activity I time taken by this times the computational slowdown index of virtual machine J. Phi W virtual machine means this denotes the scheduling of all cloud activities of workflow on virtual machine. Now, schedule cloud activity I, virtual machine J, start, end. In this start and end are the start and end time of cloud activity I in virtual machine J. Now, since cloud environment is a changing environment, virtual machines are instantiated and destroyed during the course of the workflow. So we cannot create a priori scheduling plan. Therefore, several scheduling plans have to be generated during the course of the experiment. Now, schedule I is less than schedule J. Is denoted like this, where ORD, order schedule I, denotes the position of the schedule I in the sequence of the schedules. Now we get to the matrix calculations. In this equation 1, it denotes the ratio between all possible execution combinations of cloud activities and virtual machines and the total time needed to execute these cloud activities. This is denoted by beta here. And now here in equation 2, the make span of all K cloud activities in a scientific workflow is calculated. In this, sigma is the number of cloud activities in the weight Q, the sigma right here. Now, average execution time in previous executions is denoted by this right here. R denotes the reliability cost, and F, virtual machine J, is the probability of given number of failures in virtual machine J occurring in fixed interval of time. In this, R has to be minimized so that it gets near 1. Reliability cost is associated to virtual machine J in this equation. In this, total reliability is equals to the sum of reliability of all cloud activities in execution. In this, gamma, virtual machine J, represents the set of cloud activities already executed in virtual machine J. Now we need to determine the network cost. Network cost is the cost of data transferring from and to the cloud. Let's assume that W reads and writes information to a shared area. This way, all possible schedules read and write same amount of data from and to the same shared area. This way, cost of reading becomes equal to the cost of writing. Now we calculate the execution time. To do so, we have to insert a new data dependency in the workflow to represent the data transferring between cloud activity I and the shared area, and from the shared area to the cloud activity J. In the second equation, we calculate the total transfer time. This is the second equation. We calculate the total transfer time for all cloud activities in the workflow. Now, total cost is based on pay per quantum of time in the cloud, which is represented by this. In this, M is the total monetary cost, and it is divided into two parts actually. This is the first part and this is the second part. First part is cloud activities execution cost, and the second part is the data transfer cost, and monetary cost is the sum of these two. This denotes the transfer financial cost, or the total amount to be paid for data transferring. In this is the value to be paid per unit of transferred data. Now we calculate the final cost function. In calculating the final cost function, we need to take into account execution time, financial cost, and reliability criteria. Now, weighted cost model is used where scientists have to inform the weight of each criteria. For each virtual machine J in a virtual machine that is idle and requests for a cloud activity, it is then performed a search for the best cloud activity I in the list of available cloud activities. Given that virtual machine J is a part of virtual machine, as the next virtual machine to execute a cloud activity, we have to find cloud activity I in cloud activity prime, which minimizes the given cost function. We need to note that the search space for this cost model is a three-objective one, since we try to find the best set of available cloud activities to execute for a specific virtual machine following execution time, reliability, and financial cost criteria. Now we get to the adaptive scheduling algorithm. Adaptive approach is composed of 4 algorithms, the first of which is the greedy scheduling algorithm. In the greedy scheduling algorithm, it chooses the best group of cloud activities to execute in a specific virtual machine. Line 3 starts by loading the list of available cloud activities without dependency. That is, the cloud activities that are ready to be executed and the list of virtual machines in line 4. Now in line 5 to 10, the algorithm initializes the virtual machines with fundamental information to generate groups of cloud activities. Line 11 then starts analyzing if there are available cloud activities to be executed. After which, in line 12, if at least one cloud activity is to be executed, the algorithm searches for idle virtual machines to execute the available cloud activity depending on the scenario. Now, if the scenario is that we have to find the fastest scheduling plan, then the algorithm orders virtual machines from least powerful, that is the ones with the smallest CSI, to most powerful, largest CSI. If the scenario is of scenario 2, in which we focus mainly on finding with least financial cost, then the algorithm orders most powerful to least powerful. Now from line 13 to 20 right here, if there's an idle virtual machine, then the algorithm analyzes the granularity factor. And this factor is then used to group available cloud activity to encapsulate in a new one. That is, group cloud activities into clusters. Now from line 21 to line 27, based on these clusters, the algorithm calculates the most suitable group to execute the virtual machine. Now, from line 28 to 29, the list of available cloud activities and virtual machines are updated. And then finally, in line 32, final schedule plan is provided. The second algorithm is of cloud activities grouping. The main focus of this algorithm is to produce new cloud activity by encapsulating two or more cloud activity into a new one to reduce communication and data transfer overhead. The challenge with this is, however, how do we determine group sizes and which cloud activities do we group together? What this algorithm does is it dynamically tunes group size based on provenance data. It can estimate the execution time of a new cloud activity, which is composed of two or more cloud activities. We also aim at maintaining the same average execution time of cloud activities associated to the virtual machine. Now, in this algorithm, line 2, it verifies if the granularity factor is null, and in this case the group is impossible to be set. Now in line 6, if number of available cloud activities to be grouped together is smaller than the granularity factor, as we can see here, it is checked here, then just one group is formed. And then from line 11 to 27 right here, if the number of cloud activities is greater than granularity factor, the algorithm generates many groups with approximate average execution time. Now we discuss the algorithm 3. Algorithm 3 is responsible for setting up the granularity factor for each virtual machine in the system. This algorithm is actually a prerequisite for the previous algorithm that we discussed. Now, as we can see, in this algorithm, the line 1, it is responsible for executing the cloud activities or group of cloud activities. And in line 3, it calculates the average execution time. And then line 4, average execution time of previous execution on the VM is also calculated. And then in line 5, if the new average time is less than the previous average time, then in line 9, algorithm increases the granularity factor. If however the new average time is greater than the previous average time, maximum granularity factor is set. Now we discuss the last algorithm, which is the load balancing algorithm. So in this algorithm, it allows the system to adapt to the amount of virtual machines to fit the deadline and the limit budget. This is done to quickly scale the virtual cluster capacity, both up as well as down. Now in line 6, as we can see here, what is being done here is that it is verifying if the throughput, which is the cloud activity per second, it is verifying if the throughput has varied. If it has not varied, then nothing changes. Then in line 3, 7 to 8, if the throughput is reduced, algorithm simulates a new make span and a new financial cost. Then from line 9 to 15, right here, what happens is that if the new make span is greater than the deadline and the new financial cost is smaller than the budget, number of virtual machines scaled up to the number of virtual machines will be scaled up to meet the deadline. Now from line 16 to line 23 right here, if the deadline is met but the new financial cost is greater than the budget, then the number of virtual machines will be scaled down. This way, the cloud activities should be rescheduled. Now we take a look at the Cumulus conceptual architecture. Cumulus conceptual architecture, it provides support for parameter sweep as well as data parallelism. Now, in the client tier, what happens is that it starts the parallel execution of the workflow activities in the cloud. Now, the distribution tier contains the encapsulator. What it does is that this encapsulator, which generated all the cloud activities to be executed following a fragmentation process or a parameter sweep. Based on this, the scheduler then defines which virtual machines receive a specific cloud activity to execute based on virtual machine's request for the cloud activity. Now, scheduler executes a proposed greedy algorithm then to determine the best cloud activity for a specific virtual machine. Now, in the execution tier, it invokes programs associated to the activities of the workflow in the many virtual machines available for use. The components in the execution tier may be deployed in more than one cloud provider. The data tier, it contains all the repositories of data used in the Cumulus, and then it contains provenance data as well as information about the types of available virtual machines. All input data consumed by several virtual machines in parallel execution. Now we get to the part of the experiment. First, we discuss how we set up the experiment. In this, we use a SciPhy, S-C-I-P-H-Y, as you can see with this right here, SciPhy workflow. It is a parameter sweep workflow and is used as a case study in this paper. Now, MapReduce is used in this. MapReduce is a programming model that aims at easing the parallelization of applications. Hadoop is the framework developed by Apache that provides the MapReduce core components, the Hadoop file distribution file system. For the experiments that follow, executed in this article, Cumulus and Hadoop have been deployed on top of the Amazon EC2. What we do in this experiment is compare the proposed adaptive approach with existing solutions that can be used to parallelize the workflow that need high-performance computing in clouds, such as MapReduce. SciPhy workflow, modeled on distributed cloud environment, is based on CentOS environment and then compared with Hadoop. Now we compared the paper's approach with the ideal curves of the scheduling and the parallel performance measures of speed up. So the first step would be to compare the Cumulus way with the proposed cost model and scheduling algorithm. Then the results achieved while scaling resources up and down are documented. Then we analyze the financial cost of executions and the data transfer. This histogram right here is the cloud activities execution time distribution, and it is developed by analyzing the provenance repository of Cumulus. That is 150 number of occurrences took 100 seconds, as you can see by this histogram. Based on this average as well as standard deviation values of each cloud activity is calculated. Now, also based on this, we can schedule more powerful virtual machines if we want better performance. We can also schedule more computer-intensive activities to cheaper virtual machines if we are focusing on financial cost. Now let's get into the non-adaptive performance and scalability analysis of Sky Cumulus. This graph here represents the execution time for scenario 1. Scenario 1 focuses on performance by setting alpha 1's value to 0.9, alpha 2's value to around alpha 2 and alpha 3's value to around 0.05. The execution time is obtained as we can see in this graph. We can notice that the result here, that the total execution time of SkyFi workflow using both Sky Cumulus and Hadoop decreases when provided more virtual machines. Sky Cumulus outperformed Hadoop when using 128 virtual cores. As you can see right here, Sky Cumulus is the one with the dotted line, and it took lesser execution time than Hadoop. So why could this have happened? So this is because Hadoop has serious overhead while generating maps, and Sky Cumulus scheduling based on the proposed cost model scheduled more intensive cloud activities to large virtual machines and less intensive cloud activities to micro virtual machines. Now this is the speed up graph for scenario 1. As you can see, the x-axis is the number of virtualized cores and this y-axis is the speed up. Now when we analyze this graph, we can see that the Sky Cumulus reached a linear speed up right here from 2 to 32 cores, then suffered a degradation when using 64 to 128 cores. Therefore, what we can deduce from this is that acquiring more than 64 virtual machines for execution may not be advantageous, especially if the number of cloud activities becomes closer to the number of virtual machines. Now this graph represents the execution time for scenario 2. As you can see, the x-axis has the number of virtualized core as well as the y-axis is the execution time. The Sky Cumulus graph is represented by the dotted line and the Hadoop is represented by the plain line. Now scenario 2, what it means is that it focuses on monetary cost by setting alpha 1's value to 0.05, alpha 2's values to 0.05, and alpha 3's value to 0.9. Now, more intensive cloud activity got scheduled to micro virtual machines, while less intensive cloud activities got scheduled to large virtual machines in this case. So the result of this is that the Hadoop, it outperformed Sky Cumulus while using 2 to 128 virtual cores. Acceptable. This is an acceptable result since focus was on financial cost, not on performance. Now let's take a look at the speed up for scenario 2. Now what we can analyze from is that Hadoop reached a better speed up than Sky Cumulus and both suffered a small degradation from 64 onto 128 cores. This result is acceptable since, as we discussed earlier, the main focus was on financial cost, not performance. Now let's discuss the execution time for scenario S3. The x-axis has the number of virtualized cores, the y-axis has the execution time in hours, and the Sky Cumulus is represented by the dotted line, where the Hadoop is represented by the full line. Now, in scenario 3, it focuses on reliability by changing the values of alphas. Now, we need to calculate the probability of a given number of failures in the virtual machines. Now, what we know is that the micro virtual machines, they degrade faster than the large virtual machines. Therefore, micro virtual machines have higher failure probability. Algorithm and cost model schedules intensive cloud activities to large virtual machines and less intensive cloud activities to micro virtual machines if we're focusing on reliability. Now, what we can analyze is that the behavior we obtain is very similar to scenario 1, and the result is that the Sky Cumulus outperforms Hadoop when using 1 to 128 cores. Now, when we analyze the speed up for scenario S3, what we notice is that the sky cumulus, it reaches a linear speed up from 2 to 16 cores, right here, and then suffers a small degradation when using from 32 to 128 cores. Now we discuss the execution time for scenario 4. In scenario 4, we give equal focus to all criteria by setting all the values of alpha to the same value of 0.33. So alpha 1, alpha 2, and alpha 3 are all set to 0.33. Now what we can analyze from this graph is that the performance reached was very similar to Hadoop. Sky Cumulus is pretty much performing the same way. The main difference in performance was probably due to the overhead imposed by Hadoop to generate maps and reducers. Now let's talk about the scalability according to the number of input files. The x-axis here represents the amount of input files, or the multi-faster files, and the y-axis is the average time. As you can see, these are the scenario 1, scenario 2, scenario 3, and scenario 4. Now, to analyze the overhead imposed by Sky Cumulus when processing large volumes of data, what the paper did was it executed sci-fi using 16 cores by varying the number of input files and the scenario. So what it varied just the input files and the scenario. This experiment actually consumed from 100 to 1600 input files. The result could be concluded as that the volume of data to be consumed increased as the execution time also increased, but overhead imposed by Hadoop also scaled up. Scenario 1, Scenario 3, and Scenario 4 present a good scalability by reaching a near linear scalability. However, scenario 2 could not scale in the same rate since its focus was on monetary cost, not performance. This table right here denotes the total monetary cost for scenario S2. As you can see, this is. Now we get to the adaptive performance analysis. This diagram here denotes the adaptive execution. As an experiment to analyze the adaptive approach where the load balancing algorithm scales the resources up and down, the authors executed sci-fi in several scenarios. One of these executions is actually presented in this figure right here. Performance analyzed by setting up the deadline as 10 hours, which is 36,000 seconds, and the limit budget was set to $150. In this execution, the number of virtual machines increase and decrease over time to meet the deadline as well as the budget. Also, the virtual machines can be destroyed without interference of Sky Cumulus. Now, we encountered 3 different cases. First is the ideal scenario, in which we know a priori that if we executed sci-fi using 16 cores, we could meet the deadline and the limit budget with the best possible performance. But the other 2 cases, the amount of virtual machines increases and decreases gradually. In the first of the 2 cases, there is no available provenance data. So the algorithm therefore has to wait for provenance data to be generated for it to be able to estimate the amount of resources. And the second of the 2 cases, provenance, it acts based on provenance data. The algorithm starts to increase the number of virtual machines earlier than when there is no provenance. Now we take a look at the level of idleness of the virtual machines during the workflow execution. Now, the result is that the Sky Cumulus takes more time to start a new cloud activity. This way, when using adaptive approach, the level of idleness of the virtual machines tends to be greater than when using a static scenario approach. However, the difference is pretty much acceptable. Now, let's conclude our PowerPoint. What we did in this paper was use parallel techniques to improve performance. Now, to increase the uptake of cloud model, new solutions have to be developed. A priori scheduling is not an option. Workflows should benefit from elasticity. Therefore, the need of adaptive scheduling approach is a must. Now, Sky Cumulus is a workflow engine to support parallel execution in clouds, and it has specific data provenance. Now, this paper proposes a weighted cost function and adaptive scheduling to explore dynamicity of clouds. It then conducts experiment results. Conducts experiments of which experiment results show that the proposed approach was able to find the efficient solutions. Hadoop was the choice for a baseline. The paper then compares the static approach with the Hadoop implementation. The performance evaluation of the adaptive execution in Sky Cumulus showed results very close to the ideal solution. There was also a good trade-off between collecting provenance and performance prediction. These are the references. If you guys have any questions, you can comment on my video below, or you can shoot me an email. Thank you.